Okay.
All right, so our next speaker is Bern, and he will tell us about from scattering amplitudes to gravitational waves.
Okay, thanks a lot for the invitation. So I'll be telling you about progress that's been made since the KITP conference on a topic that was eagerly discussed back then. There was very little work back then, but people were already excited. So mainly I'll be talking about work that I did with Clifford Chung, Radu Roiban, Xiaoshen Chen, Mikhail Salon, Mao Zhang, and then also Andres Blum. So we all know the excitement of the discovery of gravitational waves. And at least for me, there was something that happened that I just found absolutely amazing, which is that for an instant, the event was brighter in gravitational radiation than the brightness of all the stars in the visible universe are in electromagnetic radiation. Now that's pretty awesome. So that seemed like a good idea for something to work on. But of course, the question is, how can we who work in scattering amplitudes help out with the core mission of LIGO Virgo? And this was already understood and discussed back at the KITP conference in 2017. And there were a number of events or talks. So there's Walter Goldberger's talk, which is very influential on classical radiation of a double copy. There's Donald O'Connell gave a very nice talk about perturbative black holes from the double copy. And there are many discussions, public and private, on the possibility of applying amplitudes to gravitational radiation. And we'll be using the double copy. We realized back then that this would be something very important in the way we think about this problem. And the KITP, I would say, was really where these ideas really started going on shell, both figuratively and literally. While we're very far away from actually having something for our friends at LIGO, at least the discussions convinced us that this was a very promising direction. And certainly one of the side effects that happened is that people in the general relativity community heard the excitement. So it wasn't that much longer afterwards. This October 2017, off in Paris, there was Thibaut Damour, where he wrote a paper, and I will read to you a sentence of the abstract. And we urge amplitude experts to use their novel techniques to compute two-loop scattering amplitudes of scalar masses from which one could deduce the third post-Minkowskian effective one-body Hamiltonian. I'll explain a little bit later what this post-Minkowskian Hamiltonian is. But there you have it, a clear invitation. Our colleagues in general relativity heard that we were excited, and they gave us a challenge. And this challenge is very difficult using standard methods, and also it's something of direct importance to the theorists who work on LIGO and Virgo, and in principle, this is something that could enter the LIGO Virgo analysis pipeline. So this really seemed like something we should focus on. But before we get to that, at first sight, this seems a little bit crazy to use amplitudes methods to discuss the problems of gravitational radiation and general relativity. There's some very obvious differences. First, in gauge theory collider physics, we think about unbounded trajectories. Particles come in and they scatter out. In general relativity, generally, for the LIGO problem, we're interested in the bounded orbit problem. And then the physics looks different. In one case, we use gauge theory, QCD, electroweak theory. We use quantum field theory. The other case is general relativity and classical physics. Now, from Henrik's talk, you understand that, of course, there's a strong connection between gauge theories and general relativity, and that's something that we would like to explore. And this basic idea that in fact, the idea that the ideas in quantum field theory are very natural for general relativity, that was actually understood long ago, Iwasaki in 1971. And then Goldberger and Rothstein, they created a formalism, a systematic formalism for thinking about this problem. And the basic idea behind it is Black holes and neutron stars are point particles as far as long wavelength radiation is concerned. If these things are point particles, then clearly those of us who do particle physics have an angle to get into the problem. And in fact, I'll show you that the scattering amplitudes way of thinking about it is in fact very well suited for pushing state-of-the-art perturbative calculations for gravitational wave physics. Oh, we're very good at gravitational perturbation theory. That's what we've learned to do in amplitudes community over the last 20 years. But there are some serious issues. We do quantum, not classical perturbation, and then the unbounded orbit problem. And I'll explain a little bit about how we deal with these issues. So what's the problem? So we want to improve on post-Newtonian theory. So when you look at the in-spiral problem for gravitational waves, then we can think of the problem in terms of three different domains: the in-spiral, the merger, and the ring down. And the part that we want to look at here is the in-spiral part. That is where you can use perturbation theory, and there's a whole technology, a way of thinking about it, post-Newtonian theory, and then you put it together with let's say, effective one-body theory or other models for getting high precision templates for the in-spiral part. And it's extremely important to have precision calculations. And the reason is because you're watching a phase in a wave, and the small errors that you make, they accumulate. So what's this post-Newtonian approximation? Well, that's pretty simple. Basically, what's done is you expand simultaneously both in G and in V square, and that's from the virial theorem. And in the simultaneous expansion, let's say you're deducing a Hamiltonian from general relativity. The first term, that's right here, that's right here, that's Newton, and then the second term that was worked out by Einstein, Nichols, and Hoffman, and that would be a correction on the Newtonian potential. And then over the years, people have systematically cranked out different orders: second order, third, fourth. The reason why people do this is because it's very important. And you can see that it's very important because LIGO is sensitive to these orders of perturbation theory. That's what's shown on this plot. And essentially, the way you should read the plot is the lower the point. If it's lower, that means that LIGO is more sensitive to it. This is just a comparison to Hulse-Taylor binary pulsar. And you can see Hulse-Taylor, they're very sensitive to Newton because you're watching it for a very long time. Of course, you win a Nobel Prize for the gravitational radiation, but you can see that LIGO is not only sensitive to the quadrupole formula, but it's sensitive to much higher orders. Okay. Now, when we started thinking about this, of course, we were wondering what problem to work on. There's a variety of problems that the ideas of amplitudes can be applied to. You can think about applying it to spin effects, finite size effects, and physics effects, directly look at the radiation, high orders, and perturbation theory. Well, we know what problem we wanted to solve. It was laid out for us by not only by Damour, but also talks from Buonanno. We wanted to solve a problem which would be very difficult to solve using the standard techniques. If you're going to enter the field, switch what you're doing, then you'd like very much to make a difference. That on the receiving end, that whatever you do is something that's useful for the people who work on this. Okay, so what's this two-body Hamiltonian at third post-Minkowskian order? That's the target. Well, that was explained very nicely at the Amplitudes Conference in 2018 by Buonanno. I stole her slide here. It's a little bit crowded, but I think it's a little better to have the slide from the authority. So what this slide shows is the different concepts of post-Newtonian versus post-Minkowskian. So post-Newtonian, 0 PN, we look down the column here, that's Newton, In here is Einstein, Infold, and Hoffman, and then so on and so forth. Higher orders in the post-Newtonian expansion. So it's an expansion simultaneously in v square. 1 over r actually means g. So it's an expansion in v square and g simultaneously. The post-Minkowski approximation, that sounds like a strange name, but we who do particle physics, we have another name for it. We call it perturbation theory. It's just a perturbative expansion in Newton's constant, order by order, just systematically expanding exactly the way we normally do with scattering amplitudes. The target that was requested was third post-Minkowskian order. So, and you can see this has not been done. And the basic idea is you're now working, in a sense, on a different axis, that you're working to fixed order in g, but all orders in velocity, so that it's Lorentz invariant. Okay, so that was the target. Now, the basic tool that we use for thinking about the gravity problem, it's double copy. And this was explained in Henrik's talk, so I won't say very much about it. It's something that's very general, as Henrik emphasized. But on the practical side, it gives us awesome calculational power. We can do calculations that would be very difficult. And the basic idea is that we can relate the gravity calculation to the simpler gauge theory calculations. And we use this to answer difficult questions where the calculations could be very hard of physical interest. For example, the 5-loop supergravity, which is used to study non-normalizability problem, the problem of gravity theories. I'm not going to talk about that. Here I'm going to talk about g-cubed corrections to Newton's potential from general relativity. So it's a classical problem, but we think about the problem from the double copy point of view. In fact, there's a small industry that's developed to study this, the connection to scattering amplitudes. By the way, I witnessed the creation of the collaboration Kossauer and Maybe and O'Connell. I walked into the office at the instant this collaboration was started, which is very nice to see where this thing led to, which is very beautiful. And then there are other approaches. There's world line approaches. There's various technical problems having to do with dilitons that people were already discussing back in KITP, and so on and so forth. But of course, what you'd like to do, the key question is, can you do something that actually makes a difference for our general relativity colleagues? So it had to be beyond the state of the art. So to be clear, what are we after? Right? So what we want to do, and this is the way our friends in LIGO work, is they replace general relativity with a two-body potential that's easy to use in the bound state problem. So if you're trying to solve the in-spiral, you prefer not to start with the full general relativity. You'd like to work with a simpler Hamiltonian that captures the essential physics that you need. You want to extract the physics juice, leaving behind the complexity of general relativity. Okay, one way to do this is using potentials Hamiltonian. Except the idea is it's compatible with general relativity to all orders of velocity and valid through a certain order in Newton's constant. Basic tool we use that was laid out in this paper, Chung, Rothstein, Solon. And the idea is to bring two communities together, the effective field theory community, the amplitudes community. We have gravitational scattering amplitudes, we have effective field theory, and then we combine these two in order to extract the potentials that our friends in LIGO desire. Now, at first sight, this might seem to be a bit inefficient because we're thinking about starting from quantum amplitudes, and then you extract classical physics. That seems a very strange way to do it. It might look inefficient. It actually turns out it's not inefficient at all, because you go to the classical limit pretty quickly. Just on the first line, you can essentially extract the classical parts. The basic idea why this might be a good idea is the efficiency that comes from almost magical simplifications for gravitational amplitudes, and then this effective field theory method, it efficiently targets the pieces that we want to extract. Now, it's actually good fun when you start looking at this problem. In the beginning, it looks like very straightforward, that if you look at the tree level, and then you're trying to extract the potential, it's very simple. You can find this in textbooks. You take the amplitude, you do a Fourier transform, and then out comes the potential. And that's very nice. But once you start looking beyond one loop, especially, things get very complicated, at least conceptually. But it doesn't, well, after a while, it becomes very clear what's going on. But in the beginning, it looks pretty confusing. From my personal point of view, in a sense, the great shock is what I learned in graduate school on H-bar counting and classical limits is completely wrong. So what you learn, at least what I learned back at Berkeley, was that every loop has an H-bar. So for example, this would be quantum, right? That in fact is not correct at all. Maybe in some sense it is correct if you do the scaling in a certain way and you count your H-bars, and indeed that's true, but that's not what the problem is. The problem is how do you extract the classical physics? And if you scale things correctly, you in fact discover that it's completely backwards. The loop amplitudes scale actually as 1 over H-bar to the loop order. They don't scale like H-bar to the loop order. And there's various issues you have to take into account, double counting and iteration. And the iteration comes from the idea that you're expanding e to the is classical over h-bar. By the way, that's where the 1 over h-bars come from. No mystery there. So when you do that expansion and you compare to the Feynman diagram, there's some double counting you have to take into account. You can start worrying about 1 over h-bars and h-bars crosstalk, and you get yourself very confused. But in fact, the effective field theory approach is the way we think about this so that it's very clean. We bypass all this confusion very simply by using effective field theory. The way the effective field theory works is exactly as you might expect. You construct a field theory of scalars. So suppose you're thinking about the spinless problem with scalars or spinning problem, then you have spinning particles. But let's start with scalars. And then you write down a relativistic theory with no antiparticles. Notice this linear time derivative. We don't want antiparticles. And then you use this theory to define a potential. This is the potential we're interested in. If we can match this theory to general relativity, then in fact, we have the potential that our friends in the LIGO community would like to have. Okay. And the way it works is you do 2 parallel calculations. One is full general relativity. That's complicated. So we take out the heavy artillery, we take out amplitudes methods, double copy, and generalized unitarity. And you always keep an eye on h-bar that goes to 0. You want to just get rid of things you know that won't contribute. Then you have to do loop integration. There's some technology for that. And out pops at the end the gravitational loop amplitude that would be valid in this potential region. And simultaneously, you do this other calculation in the effective field theory. There, it's much simpler. Just use Feynman diagrams and just crank away, and you get an amplitude, an effective field theory amplitude. You demand these 2 are equal, and in that way, you determine what the potential is from an ansatz. So you do this for a generic potential, and then you match the coefficients. If you get a match, then you know what the potential is, and you're good to go. So just, I'm not going to say too much about exactly how we did this, but let me just make a few points about general relativity, unitarity, and the double copy. So the first thing you realize when you start thinking about this problem is that we're only interested in long-range forces. That means that the 2 matter lines must be separated by on-shell gravitons. So these gravitons here, they need to be on-shell. And then you realize that if you're interested in the classical potential, in fact, you just have to pick up an energy residue. It's not too surprising because you shouldn't really have a 4-dimensional loop integral. It's just a residue that you pick up. So you get another cut here. And that means that we're in unitarity heaven. This problem is designed perfectly for the unitarity method in the sense that we're very naturally thinking about on-shell quantities right from the very beginning. So, okay. When you go to higher order, let's say you go to the 2-loop case, the idea is the same, that there has to be a cut, a unitarity cut. Oops, these are on-shell gravitons, such that the 2 matter lines, these solid lines, are separated. And in fact, it turns out there's only 3 cuts that have to be evaluated, plus permutations. So the tools that we have, the amplitude tools, they fit very naturally. You anyway would like to think about unitarity, generalized unitarity. Maybe just one quick thing about how we use double copy. So this would be the KLT version. In the calculation, for technical reasons, it was better to use the BCJ version so that we could deal with d-dimensional regularization subtleties. If they turned out there weren't any subtleties, but you can only prove that by doing it the hard way. But in any case, here's the KLT way of doing it. So let's say you have a certain cut. So there's a 3-point amplitude, 3-point amplitude, 4-point amplitude, and we want this for gravity. What we do is we have a sum over the helicities of these gravitational amplitudes. You use KLT, turn it into Yang-Mills amplitudes. And then these Yang-Mills amplitudes, if you're using 4-dimensional helicity, they're extremely compact objects. Okay, and then to make a long story short, you then have to integrate these cuts. So at 2 loops, you have to integrate these cuts. But there's a machinery for doing this that was laid out in the paper of Chang, Rothstein, and so on. So we just followed that and got the answer. There's the answer. So this is the amplitude. So this is in the classical potential limit. So this amplitude is only valid for the purpose of extracting the potential. It's not even necessarily the classical amplitude. It's just capturing all pieces where the potential, where you're getting the potential. And it has, there's an arc cinch here. That's just a logarithm. Not too surprising, there'd be a logarithm there. And this is in terms of certain kinematic variables that are defined here. There's these 2 functions. These are infrared singular functions, F1 and F2, which it turns out we don't even need to know them because they cancel at the integrand level in the EFT matching. So we actually never needed to evaluate it, but it's straightforward enough to evaluate it in dimensional regularization if you're interested in that. And the one thing that you can look here is that it's a surprisingly simple answer. It may look a little bit complicated, but you know what happens at multi-loop general relativity. So this is quite a nice result. But of course, this result is not what our friends in LIGO want. We can admire it, but it's not useful. You have to go to the potential. That's done through the EFT matching, which I think is still the most powerful way of doing it. It's certainly the most straightforward and offers a lot of clarity. And the answer for the potential is just in terms of some coefficients times corrections to Newton's potential. Inside here, C1, Newton is in here. This includes the all orders in velocity. That's why you don't recognize it directly as Newton. And then C2, a piece of this is what Einstein, Intold, and Hoffman found. And then C3 is the new piece, all orders in velocity. Now, what was a very important question for us is how do we know this thing is right? We do this calculation and use all these fancy ideas, and then at the end you get an answer, but how do you know it's right? Well, the most important check we had was comparing to the post-Newtonian expansion. So the idea is we take our answer and we expand in velocity, and then we start matching. Of course, you can't match directly because everybody's working in a different gauge, but it's straightforward enough to look for a canonical transformation, a brute force canonical transformation between our result and any result in the literature. And in fact, this works, and that proves, at least through this order, the overlap region to the fourth post-Newtonian order, that in fact we're correct. And then we've had various other checks, for example, looking in the small mass, the test mass limit, it matches the Schwarzschild Hamiltonian. And then in the heroic effort, Bini, Damur, and Geralico, they verified our result through sixth post-Newtonian order. So that's very nice. So we're quite confident this thing is correct. It's gone through a set of checks from people who were sufficiently skeptical to really want to find an error, and it's holding out. Okay, just one little thing I want to show you about the comparison, because it's a little instructive. So our formula back here, you might say, well, that looks like a little bit of a complicated formula, but it has a certain nice, pleasant structure to it. Right? If you now look at the way post-Newtonian works, it's much more complicated. In fact, it keeps on going. Our expressions don't have all the terms you'll find, let's say, fourth post-Newtonian order, because we're missing higher order and G terms, because that's not part of our calculation. We only work through order G cubed, but there's still most of the terms overlap. Now you can ask, why is their expression so much more complicated? And there's, of course, a simple answer to that. One is that it's expanded. When you take a simple formula velocity and expand it, it makes a mess. Also, you have to do appropriate gauge transformations to clean this up. I'm almost done. This is near the end. So, of course, we were, of course, very interested in seeing what our friends over at LIGO collaboration would do. Actually, 8 days after our paper, there was a very nice paper that had a look at trying to use our Hamiltonian to build better models through this effective one-body approach, and to test it against numerical relativity, which is taken as the truth. I have to say, I find it a little hard to interpret this because, for example, these models, they don't account for the gravitational radiation, but when you're comparing against numerical relativity, it does account for it. So I'm not quite sure what to make of this comparison, except let me just say, quote something from their paper: this rather encouraging result motivates a more comprehensive study. So we've definitely gotten the attention of our friends. The most exciting part is that the methods are far from exhausted. We're looking at the next order, of course, and in fact, there's much greater improvements on the horizon. There was a recent paper from Para Martinez, Ruth, and Zhang, where they found much better ways of doing the integration than what we had originally done. And there's many topics to which these ideas can be applied, higher orders. You can start thinking about resummation in Newton's constant once you have enough information. Radiation, finite size effect, spin, there's really a lot of activity on that, and that includes a paper from us. And I think in the coming years, we can definitely expect many more advances. So the summary is that the amplitudes methods, they give us a new way to think about problems of current interest in general relativity. This double copy idea, it's a unified framework for thinking about gravity and gauge theory. There's a variety of problems we can apply it to. Henrik spoke about many problems. Here I spoke about one specific problem, which is the problem of gravitational radiation in bound state systems. And I would say that the KITP workshop is really where the ideas for really looking at this seriously was planted. There were a number of papers from, especially from Walter Goldberger and colleagues. But that's where people really started discussing the real possibility of doing something useful for our friends in the general relativity community. And the way we approached it is by combining EFT methods with the amplitudes methods, and it gives us a powerful tool for looking at the problem of gravitational wave physics with the output that LIGO Virgo theorists can use, and specifically we obtain state-of-the-art results, the order G cubed Hamiltonian, There's also work on spin, and there's many topics that you could apply these types of ideas to. Resummation in G, spin, finite size effects, and radiation are obvious directions of, I think, people, including us, will be working on in the coming years. And we should expect many more advances in the coming years, not only for gravitational wave physics, but more generally for understanding gravity and its relation to the other forces through the double copy. And I think it's time for a new workshop. Okay, thank you.
Thanks, V, for a nice talk. Are there any questions? There is one. Arkady.
Okay, so thanks for the talk. Okay, nice to see you, Tzvi.
Oh, hello.
What I wonder, about this gauge dependence, that in certain sense, when you are talking about gravity, then, the choice of your experimental device, it's part of your gauge choosing, because you see, it's not what you're measuring, it's in certain sense, it's your gauge, right? The way you measure.
Right.
So I'm not talking about, kind of internal gauge for calculating loops or whatever. I mean, it's clear there, but I wonder if you have any problem of this type, because you should accommodate yourself to real purpose of measurement in certain
things. So one point is, so when we're doing the measurement, we're very, very, very close to flat space.
Yeah.
So in some sense, well, in a sense, this has nothing to do with what we do, in the sense that we're matching onto the, you could say, standard way of doing it. And I'd say one of the key facts that makes it less problematic, this issue you're talking about, is the fact that we are really in flat space with a strain of 10 to the minus 21. So it's completely, by the time we're measuring anything from this, at the final output at the detector, right, the strain is 10 to the minus 21. So we are as flat a space as you could imagine. so I think there's you could definitely get yourself extremely confused if you started thinking about, let's say, measurements closer to the emission. Then I think you could get yourself extremely confused. But I think at least for this particular application for LIGO, we're quite safe from any kind of confusion like this because we're in flat space.
Okay, thank you.
Are there any other questions?
Can I ask a quick technical question, Zvi?
Sure.
You mentioned that in
sorry, we lost you. Nima? What happened?
I'm not responsible. I didn't do it. Nima?
Radu, it is your magic.
While Nima's coming back.
So, Nima?
Maybe he's back.
Well, he should be back.
Okay. Can you hear me okay?
Yes, now we can.
Great. So I'll just ask quickly. So you mentioned that this check was done by finding the canonical transformation that maps one Hamiltonian to the other. But wouldn't it have been sort of easier just to compute an observable like the scattering amplitude with the other Hamiltonian and just see that they agree?
Absolutely right, Nima. However, in our first paper when we were doing this, it was very important that we speak the language of people who don't know about amplitudes. So had we told our friends in the general relativity community that we agree because the amplitudes match, they probably would have said, and okay, what is that? What am I supposed to take of that? What they want is the canonical transformation.
But so maybe I can ask that.
However, by the second paper, we said, it's too much trouble to, so this would be on spin. We said, it's too much trouble to bother with the canonical transformation. We'll just check it by doing exactly what you said. So
maybe a related question. There must be the analog of field redefinitions or canonical transformations. There's a lot of redundancy in these Hamiltonians, which when you think in terms of what the amplitudes are, you should get a sort of natural basis. Is the basis that's natural from the perspective of the amplitudes the basis they're using, or how do they choose their, presumably they deal with this redundancy issue. How do they fix the canonical transformation redundancy?
Well, it's just some gauge choice. I forgot which gauge they use here. This might have been the one that's on the screen. This might have been a harmonic gauge.
I see. So it's just a difference in gauge.
Yeah, they just. Okay. It's all these calculations. Let's say a Hamiltonian, like you point out. Look, this is not a physical quantity, so it all depends exactly on how you did the calculation. When we do the calculation, for example, these n dot p terms, they turn out to be identically zero. They just manifestly don't contribute, at least in the spinless case, they don't contribute to the amplitude. So we would never have such terms. But in a sense, it's just, you know, someone makes a choice at some point. For example, we make a choice. We don't do it in terms of gauges, but there's a very specific place where effectively we're choosing a gauge, which is we take the amplitude and we define it to be off shell in order to construct the potential. And at that instant, we've effectively made a choice, something like isotropic gauge. It might be even exactly isotropic gauge, but
yes,
but it's equivalent to making some kind of gauge choice. We make that choice not because we say, oh, we need to gauge fix. We make that choice because we say we want a compact, clean answer.
But in principle, you could, I mean, if you wanted to choose their gauge choice, you could have just matched, you could have just determined all their coefficients by matching to the amplitude?
Yeah, or vice versa. The way that, in fact, the original checks, or the easiest checks for verifying the answer is not through a canonical transformation. You take their Hamiltonian and you feed it through the EFT and you match the amplitude. And in that way, you could very easily, you know, match it so that even off-shell terms match up. So we could force it into their format at the amplitude level. It would be some messy thing that you have to do, some kind of ansatz, and then you try to match. It would be like calculating the amplitude without going on shell, and then you try to match at that level. So we could directly try to reproduce their answers. But
I just didn't understand what you meant by going off shell with the amplitude. I mean, so there's the amplitude, and then there's this, yeah.
I can show you explicitly, I think. I had it on a slide. It was, oh, sorry, I went too fast. Just give me a second. Yeah, right here. So on the right hand side, that's an on-shell tree amplitude. On the left-hand side, whatever that is some off-shell quantity. So I could have added things to the right-hand side that vanish on shell, and then it would affect what I'm getting on the left-hand side for the potential. But when I plug back, I use this potential to now work out an amplitude through the EFT, and all that ambiguity needs to drop out if I made no mistake.
That's what you meant. I mean, that's what you would just call right. Okay, fine.
Yeah, that's what I meant by going off shell. It's essentially this equation right here.
Steve.
Yes. Can you hear me?
Yes.
Yeah. Hi, Steve.
Hi. Good to see you. I don't know if you can see me, but I can see you. So a question, these corrections are presumably something you can see in the in-spiral, but when you get to plunge and merger, then there are going to be other important corrections, and presumably you have to go beyond this analysis. So have you thought about any methods to go after that, resummation or other kinds of ways of attacking
only
plunge and merger?
Yeah, only in a vague sense. So, well, So the way it currently works is you could say there's 3 distinct regions that people use. You can use the numerical relativity for the whole thing, but that's expensive. But at least the way we're approaching it right now, the merger is not that you could say we're not using the right language. The EFT language would break down. On the other hand, you could approach it from the other side. This side, the ring down, it is perturbative.
Yes.
And you could think about approaching, thinking about double copy, thinking about how the ring down works, and try to work the other way towards the merger. I think that'd be more fruitful, but we haven't really thought about this beyond the vague, oh, it looks like we could do something. I think on the ring down side, you could definitely do things that should be pretty straightforward and interesting. And that's based on this observation that black holes, either the Kerr black hole or the Schwarzschild black hole, can be described by double copy. So there'd be a very natural way for us to think about this problem. But so far, nothing has been, as far as I know, nothing's been done about this. But I think it's a very interesting problem.
I guess with the picture you're showing here, you're not distinguishing, there is basically another refinement of the infall. You have in-spiral, plunge, and merger. And, plunge is something where you might also expect to make some intermediate steps. Merger, of course, is going to be hard because that's pretty non-perturbative, but plunge is starting to be, a pretty significant departure from the Newtonian case, I think. And I'm wondering about there.
That plunge, it's one cycle, and then it's over.
Yeah.
But in any case, I think, well, for that, one would probably need to think a lot about resummation. There's of course a whole technology of resummation through this effective one-body approach. So there are ideas of how to take information that we use for the in-spiral, whether it's post-Newtonian, post-Minkowski, and to improve upon that so that you can really get very close to the actual merger and still are using perturbative input plus some numerical tuning, but then you're using models based on this perturbative input in order to discuss the in-spiral. So there is to discuss the plunge. So I think there is you could say, like a way forward to be thinking about it, because people have anyway taken perturbative information and tried to get as close as they can to the actual merger.
Yeah. Well, okay. Yeah, that would be interesting. In particular, it's maybe only around one cycle, but, that's towards the really interesting regime where you're forming a new horizon. So
yes,
thinking about it.
Indeed. Absolutely.
One last question before the open question session. Lance?
Nice V, nice talk.
Thanks.
Yeah, you have to make a canonical transformation if you want to compare at the level of Hamiltonians. But like on slide 23, you said there was also comparison at the level of classical scattering angle.
Right.
One question is that completely unambiguous? In other words, if you have two Hamiltonians that give the same angle, are they related by a canonical transformation? So they're basically the same thing. And then the second question is, can't you also use this approach of Kalin and Porto to directly map from the, gauge invariant observables, like the scattering angle, to the periastron advance?
Yeah.
And, carry it over into the bound state that way?
Well, the answer, yes, you can. However, the little problem is that as far as we can tell, it only works in the spinless case for this problem. And to actually do that to, let's say, a more general problem, it's not that helpful. So after the fact, you could say after the fact, we know that in fact the angle has all the information in the Hamiltonian as in the papers from Porto and our friends and Niels Bohr who explained that. But in a sense, you could say what might be more important is not what you could do for the problems that we already understand. It's for, can you now take that idea and can you push it to the next level of problem? For example, spin. And
Well, you
that,
need more observables in the spinning case, obviously.
yeah, but
In the spinless case, you stay in the plane. In the spinning case, you have other angles, which is out of plane, and you have the spins themselves asymptotically, and the analogs for bound states too, I guess.
Let's just say that's not the only complication. Yeah, that definitely makes it a lot more complicated. But on top of that, it does not work. Look to work in any simple way that at least we could tell. But yeah, thanks. I mean, I didn't want to. Yeah, actually, I have to say I was thinking about adding that to my talk, but then I decided not to, because of the worry of whether you can carry it to the next problems, and it doesn't look that way to us.
Just remember, on shell good, off shell bad.
Yep.
So
I know except there's another rule. That rule is correct, but there's another rule. If you're going to enter a new field, you need to speak the language of the people who are already there.
For a while.
For a while, indeed, just for a while.
if there are no more questions, let's thank the speakers again.